Okay, so we're going to go ahead and continue. Oh, I should probably put the microphone on me, right? Hold on a second. Hold on. I forgot to actually wear the microphone. There we go. So we're going to go ahead and continue Unit 13, talking about solving exponential and logarithmic equations and inequalities. Today's lesson is going to be focusing on quadratic style things and then their applications. Looks like that's all that we're going to be talking about today. Yeah. All right. I love these kinds of questions because they don't look like quadratics, but they are. They are quadratic exponentials, quadratic logarithms. There's just a lot of fun going on here. And by fun, I mean nerd fun. I really like these kinds of questions. So you might be looking at this going, Mr. M, how could you possibly recognize this as quadratic? And I go, well, first of all, looks to me like there's a multiplication in this exponent here. So it helps to know your exponent rules, and multiplication of exponents occurs when you have power to a power, which means this could have been rewritten as e to the x quantity squared minus 3 e to the x minus 4 equals 0. And if you're still struggling to see that it's quadratic, or could be treated like a quadratic, why don't we make a substitution? And using a substitution is a very powerful problem-solving strategy that you'll use a lot in calculus. So we might as well get used to using it now. How about, I'm going to choose the letter m because that's like the best variable on the planet. Because, you know, McCutcheon. Anyway, if we write it like this, instead of saying e to the x, we say m, what we're going to have is m squared minus 2m minus 3m, excuse me, minus 4 equals 0. And you could solve this by factoring, I think. Yes, because there are two numbers that multiply to negative 4 that add to negative 3. They're negative 4 and positive 1. So we have m minus 4 and m plus 1 giving us 0. Solving by factoring tells us that m is 4 or m is negative 1. But here's the thing. We're not solving for m. We're solving for x. So we have to undo the substitution that we did a moment ago. And instead of saying m equals 4, we say e to the x equals 4. And instead of saying m equals negative 1, we say e to the x equals negative 1. And now we isolate our x's. How do we get this x alone? Natural log of both sides. Yep. So if you take the natural log of both sides of this thing, what you'll get is x is the natural log of 4. And if you try to do the natural log on this side, what you'll get is a domain error on your calculator. And that is because the argument of a logarithm must be positive. So the answer is the natural log of 4. Ta-da! Whatever that equals. But there you go. It's natural log of 4. You guys want to ask me anything about a question like that? You mean in orange? I said m was e to the x. That way it was easy to see this was quadratic. I solved for m, and then I remembered that I'm supposed to be solving for x, so I re-sub in for m what m equals e to the x. And there it is. Natural log of 4 is the only answer. Ta-da! What'd you think? Scary hard? Not too bad? Okay. Number 10 is fun. You guys like fractions? So what are you going to do? Multiply by 2 on both sides. Let's start there. We're doing the second question. Now what? If you subtract the 16, you're going to have e to the x minus e to the negative x equals negative 16. I didn't hear anything squared, though. Ah, this. Yeah, this is actually a fraction. Now what? To the x. Multiply by e to the x, yes. That way you do not have a fraction. That's going to give us e to the x quantity squared, which is e to the 2x, minus 1 equals 16 e to the x. And now you want to bring this stuff over, like you mentioned. Somebody said it. So we have e to the x quantity squared minus 16 e to the x minus 1 equals 0. And that doesn't factor. So how would we possibly solve a quadratic that doesn't factor?
We squared the quadratic formula.
Quadratic formula. Now, normally the quadratic formula would say x equals negative b, yada, yada, yada. But we can't do that because our variable isn't x. Our variable is e to the x. So we're still using the quadratic formula, but we're saying e to the x equals negative b plus or minus root. Okay. This way we're not having to make the substitution. And the only reason why I bothered making the substitution is that way you would know and love and trust that, yes, this is quadratic. But since it's obviously quadratic because one of the expressions is squared and one of them is not, and we know that the variable expression is e to the x, not x, let's just go ahead and get our quadratic formula. Negative b plus or minus root b squared minus 4 times a times c all over 2a. And since a is 1, it's just 2. So this is 256 plus 4. That's the square root of 260. How did I do that in my head? Because I know that 16 squared is 256. So is there a perfect square that goes into 260? No. Yes.
16.
I don't think 16 goes into it, but 4 does.
264.
You guys know do you know the divisibility trick for 4?
No.
You look at the last 2 digits of any number that's more than 2 digits. Is 60 divisible by 4? Yes, then 260 is divisible by 4. Because every 100 is divisible by 4. So all you have to worry about is the last 2 digits. So yeah, that is divisible by 4. It's going to be 4 times, what, 65 it looks like in my head? 4 times 65? Yes. And 65 is 13 times 5. So it's going to give us this. 16 plus or minus the square root of 4 times 65 all over 2. Square root of 4 comes out as a 2. 16 plus or minus 2 root 65 all over 2. Now tell me, how would you isolate the x? Oh wait, we can reduce this, can't we? 8 plus or minus the square root of 65. There we go. How would you isolate the x? The natural log, the ln of both sides. However, the argument of a logarithm cannot be negative, which means this number cannot be negative. What do we know about the number 65? It's bigger than 64. The square root of 64 is 8, which means the square root of 65 is bigger than 8. So 8 minus the square root of 65 is negative. You can't use that then. So you see how we did that without a calculator? I don't know what the square root of 65 is, but I do know it's larger than 8, because 8 squared is 64. So 8 minus the square root of 65 is negative. And an exponential function that is not shifted up or not shifted down can never have a negative value. Therefore, when you take the natural log of both sides, you will get x equals the natural log of, and you can't use the negative one, so it's just 8 plus the square root of 65, whatever that is. Who cares what it is? That's the answer without a calculator. So I can have a question like that on a no calculator test. You need to know the quadratic formula. You need to be able to estimate square roots. You need to know that the argument of a logarithm cannot be negative, so you can't take the natural log of both sides if it's going to be negative. Things like that. Cool? Wasn't that fun? Oh, look. Quadratic type logarithms. Someone please tell me what I am not allowed to do as my first step. What do you mean you can't mess with the subtraction? Dang. You mean you can't cancel a logarithm? Yes. So we cannot cancel a logarithm until it is alone.
And there's a 2.
There's a 2 here. And there's a plus between two logarithms. So again, we cannot cancel a logarithm until it's alone, which means we have to condense on this side and we have to move this 2 to the exponent position on this side. So because there's an addition between two logarithms, I have to multiply these two arguments. That's going to give me the natural log of, oh, I'm going to do the distribution in a moment. Remember, the argument of a logarithm cannot be negative. So we already know that if we get a negative answer, it's extraneous because this argument is simply an x. So just thinking ahead. Anyway, now that I have a logarithm alone on both sides of the equation, I can cancel with exponential base e. Now I'm allowed to do that. When you do the distribution process here, I'm going to say, since this is AP, I'm assuming you all know how to distribute, you will get 3x squared minus 5x plus 2 equals x squared. And you cannot solve a quadratic unless it's equal to 0. So subtract x squared. That gives us 2x squared minus 5x plus 2 equals 0. And lucky for us, this does factor. I don't care what method for factoring that you like to use. Pick one and stick to it. I'm a fan of the Lizzie method. I see that 2 times 2 is 4. And the two numbers that multiply to 4 and add to negative 5 are negative 1 and negative 4. So for me, it's going to factor as this. Negative 1 and negative 4 over my a value. This is the Lizzie method for factoring. The reason why I like the Lizzie method for solving is because it gets me to my solutions for x one step earlier. Now, I'm not technically finished factoring until I move this 2 in front of this x. So it would have been 2x minus 1 times x minus 2. Excuse me. But since I'm solving for x, I can see that x is positive 1/2 and x is positive 2. Okay, well, we didn't get any negatives, which means we don't instantly see anything extraneous. But if you plug it in, you can't use x equals 1/2 because it gets you a negative argument here. It also gets you one here, but it doesn't matter. If it fails once, it fails. So this one is extraneous. 3 times 2 minus 2 is positive, and 2 minus 1 is positive. So x equals 2 is the only true solution. Wasn't that fun? Next. Yeah, because 1/2 minus 1 gets you negative 1/2. I'm going to pause the video while I'm waiting for people to catch up with me. Just like the last one, I can't cancel the logarithms until they're alone. So just like the last one, I'm going to condense. That's going to give me a, I'll start in green. Nah, I'll do this in purple. Log base 3 of x times x minus 8 equals 2. And now you can cancel the logarithm. Use exponential base 3 on both sides. Just be careful, because on the right side, that's 9. So I have x times x minus 8 equals 9. No Lizzie method required for this one. X squared minus 8x minus 9 equals 0. It factors perfectly. Oh, and look, because one of my arguments is x, anything negative will instantly be extraneous. So we can see that. The two numbers that multiply to negative 9 and add to negative 8 are negative 9 and positive 1. Okay. So that gives me x equals 9, and it gives me x equals negative 1. And we just have to make sure that our argument remains positive. Negative 1 is... Sorry. I'm not sure what happened to my brain. Regardless, negative 1 is not allowed because it makes this argument negative, and 9 is perfectly allowed. So we are ready to rock and roll with 9 only. This one happens to be extraneous. Mr. M, is there always an extraneous solution? No. Is there always one solution? No. There could be 0, there can be 1, there can be 2. That's why we always check. Ready to move on to applications of these things? I mean, that probably means we're going to be using our graphing calculator, if I had to guess. All right, let's see. Unpause at the perfect time. Let's see what's up with these applications of stuff. Applications. You have deposited $1,000 in an account that pays 6.5% interest compounded continuously, which means you've got this formula, 1,000 e to the 0.065t. It says use this formula to find the time requires, it's probably supposed to say required, for the balance in your account to double. So you could either set it equal to double the principal, or you could second trace intersect using the two graphs. I say we set it equal to double the principal and solve using logarithms, because we now have that ability. You should have that ability from last year. But let's do it this way. If I know I'm trying to double my money, then I know that it's trying to go to $2,000. But what about this? What if I never told you how much money you started with in the account? Would that change the answer? Would that change the time to double? No. And the reason why is because double the principal is 2p. I don't know why I put a negative. Pretend that's not there. So if this was 1,000, that would be 2,000. The very first thing we would have done is divided both sides by 1,000. And when we divided both sides by 1,000, it's the same as if I divide both sides by p right here. I'm going to get this. 2 equals e to the 0.065t. So it actually doesn't matter how much we started with in the account if all we're trying to do is solve for a time of doubling or tripling or something like that. What you started with doesn't matter. It's going to take the same amount of time to double as if you'd started with $1, if you'd started with $1 million. Doesn't matter. Same time to double. Let's get t by itself by hand. What are we going to use? Natural log, the ln of both sides. That is going to give us the ln of 2 equals 0.06 5t. And I think it's really obvious that we just divide both sides by 0.065. So t is the natural log of 2 over 0.065. And it is time. This is AP. We'll round to 3 decimals. Natural log of 2, close the argument, divided by 0.065 is less than 11 years at least. 11.664 years. Question. It does 10, sorry. Question. If I had said, what's the minimum number of years your account would need to be, or your money would need to be in the account in order for it to double, what would the answer have been? 11. If I had said the maximum number of years before the account doubles, you would have said 10. So depending on the words, we may have to change our answer. If this had said 10.1, and I said, what's the minimum number of years in order for your account to double? You still would have said 11. Because at 10 years, you would have been less than double. Just depends on the verbiage. This one says find A inverse. Well, I guess we should probably find A of t first, right? We know, oh, it's up above. We know A of t is 1000 e to the 0.065t. Finding inverse, what's the very first thing I need to do? Switch our x and y. Yes. Now, our x is actually t, and our y is actually A of t. If you don't mind, I'm going to not say A of t, I'll just say A. You guys all right with that? So, because I'm not going to switch my x and y, I'm going to switch my A and my t. So t equals 1000 e to the 0.065 a. So in order to solve for a, we're going to do the same thing we did a moment ago. We're going to divide by that principal first. Trying to get the a alone, and at the end, that'll obviously be a inverse of t, because now t will be our variable again. So we divide by 1000. E to the 0.065 a is t over 1000. Now what? Natural log, the ln of both sides. And to get a alone, divide by 0.065. So a inverse of t is the natural log of t over 1000, all divided by 0.065. So what does this function represent?
The amount of money and then
Okay. This formula represents the amount of money that we'll have after a certain amount of time.
Oh, the certain amount of time.
Adam? Oh. Yes. So this one, rather than saying how much money we have after time, this one tells us how much time it takes to reach a certain amount of money. So A inverse. Well, here's what we know. It's logarithmic, right? And since the numbers are so grody, we can use our graphing calculator. We are on a scale from 0 to 3,000, and my y values are from 0 to 18. Looks like we're counting by twos. Y equals, oh, I got graphs in here. Let's clear those out. the natural log of, we can't do t, so do x, divided by 1,000, divided by 0.065. Go to your window. So we're going to go from 0 to 3,000. And the scale in this graph is going by 500s. And from 0 to, I'll go 20, it's going by 2s. I'll say that that's a 20 up there. What's from 6 to 9? Oh, I thought you were talking about on my graph. Oh, okay. She's talking about something that has nothing to do with what I'm doing. Graph. Oh, isn't that fun? Okay. Oh, it even said to go from 0 to 20. Ha, like a boss. Well, it appears as though at 1,000, I'm at 0. That should make perfect sense to you because 1,000 over 1,000 is 1 and the natural log of 1 is 0. So yeah, my graph begins at 1,000, 0. And if you want a really good scale, because it does say from 0 to 3,000, or not a scale, really good graph, I can't remember if I've taught you how to do this or not. You know what? I'll just go to the table. Uh-oh, my table isn't pretty. Second table set. Begin at 1,000 and count by 500s. Just like the scale of our graph. All right. So 1,000, 0, 1,500, 6 and change. $2,000, 10 and a half-ish. $2,500, 14. And 3,000, almost 17. Now, technically, if this was an IB question, putting this arrow on the end of it would have lost me a point. And the reason why is because this is a restricted domain with brackets, meaning this is where the graph comes to an end. But I don't think that that's what was intended when this question was written. So, and here's why I say that. Because the money in our account can continue to grow. So it says find a inverse of 1,500 and explain the meaning. Well, we already did that. It's 6.238. So we used our table for that one. So when it says explain the meaning in the context of scenario, it means you will have $1,500 after 6.238 years of growth. That's pretty easy, right? Or you could say it will take 6.238 years of growth in order to reach $1,500. It really doesn't matter. It's the same information, just said backwards. How do you feel about that? It's not too bad, is it? I feel like solving these things by hand is the harder part. Applying them, you know you're going to get to use a graphing calculator, so life is good. They're powerful. Uh-oh, approximating solutions. Uh-oh. Remember when I was showing you in the last lesson about successive approximations? And I was showing you how we could approximate answers by adding more decimals? Here it is. Equations that involve combinations of exponential or logarithmic functions and or algebraic functions can be difficult to solve by algebraic methods. Let's take advantage of technology with these examples. says complete the table to find the interval containing the solution of the equation, then use a graphing utility to graph both sides of the equation to estimate the solution, round answers to 3 decimal places. Okay, whatever. Calculators, so go to your table, or your graphs, excuse me, y equals menu, and type in E, so second ln raised to the 2x. Now, clearly, I just goofed around with my table, right? I just goofed around with my table, so I'm going to go to second table set. I'm going to tell it to start at 1.8, and I'm going to have it go by 0.1s, because that's what this scale is going by. So second table set, change it to 1.8 and 0.1, and second table, and we're going to fill this out. 36.598, 44.701, 54.598, 66.686, and lastly, 81.451. Now let's look at the question. It wanted us to figure out when it equals 60. Well, 60 happens to be between those two numbers, doesn't it? And it's basically the average of these two numbers. Darn near the average. Look, this is 6 below 60. This is 6 above 60. It says round to 3 decimal places. So let's complete the table. Graphing utility. Yeah, it looks like it's going to be between 2 and 2.1. So I'm going to go back to my table set. And I'm going to tell it to start at 2. And I'm going to not tell it to go by 0.1s because we know it's going to happen between 2 and 2.1. I'm going to have it go by 0.01s. And what I'm going to try to do is I'm going to try to look for, we know it was between these two numbers. I'm going to try to look for the one that's closest to 60. Oh, look at that. It's clearly going to happen between 2.04 and 2.05. We know what happened between those two x's. So go back to the table set. I'm going to start this one at 0.04. And I'm going to have it go by 001s because it said round to 3 decimals. And we're going to get to as close to 60 as possible. Somewhere between those two, right? And I'm gonna say 2.047-ish. How you feel about that? 2.047? Yeah. Or instead of second trace intersect, we could just take the natural log of 60 and then divide your answer by 2. I'd rather do that. Take the natural log of 60. It gets me 2x equals the ln of 60. So I know that x is the ln of 60 divided by 2. I'm sorry? Then second trace intersect, yes. This is faster than second trace intersect. Natural log of 60 divided by 2 is 2.0471. So yeah, we did a good job. Oh, you can't see it. Sorry. 2.0471, so 2.047. Confirmed. Look how smart we are. Let's do it again. Let's do it again. Two, math. Oops, I pressed alpha. Math, log base, 3 of 0.5x. I'm going to reset my table. Table needs to start at 8. And it needs to count by 1s. And we're going to see where we are. Was it 524? 2.738. 2.93. 3.104. And lastly, 3.262. Oh, we're trying to figure out when it equals 3. Clearly between those two numbers. Table set. going to have it start at 10, and I'm going to have it go by 0.1s. Trying to get to 3. There it is. Look, happens between those two numbers, 2.3, 10.3 and 10.4. Second table set. Start this bad boy at 10.3 and go by 0.01s. Oh, look at that. Yeah. I'm going to say we could safely call that 2. Ooh, you know what? I don't know. We know it's between these two, right? So 10.39. And have this count by, bless you, 01s. Last time. Okay, I'm going to call it 10.392. Because look at that, 4 9s, 10.392. But if we wanted to confirm, we would divide both sides by 2. Then we would exponential base 3 both sides. And then we would double both sides. $10.392. There it is. So yes, we could solve using successive approximations, or we could just use logarithms, natural logarithms, exponential bases, or we could just set the graphs both on the same grid, second trace, intersect. Whichever one you're most comfortable with, but I want to make sure that you have all the skills. And then lastly for today, this says solve algebraically and then check using a graphing calculator. Yowza. All right. Just like we did earlier in the lesson, we said we don't like fractions, right? Multiply by 2. That gets us 3 to the x minus 3 to the negative x equals 10. But remember, this is a fraction. Multiply both sides by 3 to the x. So that gives us 3 to the x quantity squared minus 1 equals 10 times 3 to the x. If you bring it all to one side, would you believe that you're going to have to do the quadratic formula again? Isn't that awful? But it's okay. But instead of saying x equals, we say 3 to the x equals, because that is our variable expression. So 3 to the x equals negative b plus or minus root negative 10 squared minus 4 times 1 times negative 1 all over to a. Well, clearly 104 is not a perfect square, but what perfect square goes into it? 4 does. It goes in 26 times. So if you divide both these by 2, what you get is 3 to the x equals 5 plus or minus the square root of 26. But the square root of 26 is bigger than 5. Which means we can't use 5 minus root 26. So when you use log base 3 of both sides, what you get is x equals log base 3 of 5 plus the square root of 26. That's what you get if you solve it algebraically. Of course, you could type it on a calculator, but whatever. That's it. You guys got this. Just in the nick of time, nerds.